system minus 2. Look at it. And let's try extend response for this. Way up there. That's crazy. Adjustment here. Yeah. It's the purple one. All right. Red one is straight, regular, just gains. Green one is when we set our poles, what did I say, 5 times faster than the closed loop ones. This one's when it's the same as the closed loop. It's much, much slower. It's causing some real problems with our estimating what our estimated states are. It's too slow. Make sense of how these things work? All right. Questions on this? Let's do something different. Well, then, here's the new B makers. Two inputs. Say it's two inputs. Okay. Main poles. Everything. I'm going to try to find some new keys on K2. After A, B, poles, and what happened? Actor can't handle this. Actor can only handle single input, single outputs. However, something you can handle. Instead of actor, in fact, often I use this instead of place or pole placement. Right? And I have 4 rows. I just proved that actor doesn't work. All right, let me see the input. But in place, window works. And what I have are gains for each input, because how many U's do I have? no, 6 gains. Now, I made both of them, my B is just 1, 1, that's why they're the same values. But if I made B something different, we should have done this. Yeah. Different numbers for each system. All right. Yeah.
So if place handles multiple input and outputs and acronym only handles single, why would you necessarily need that or use acronym?
I generally don't. I don't use place. Place is actually an algorithm a little more accurate too. So if I have some numerical issues of like really small numbers or really big numbers, place is a little more accurate. It's usually a very similar algorithm, but it's set up for multiple algorithms. But we talked about accurate in class. Right? It's the same sort of algorithm. Right? What about multiple outputs? Right? We have this too. So let's say we have 0 and 0. We have right 4. And again, after help this, right? But place can. So our controller is going to be exactly the same. This is going to affect the observer. So let's find the observer will be place. Setup is exactly the same. Again, it'll give me 2 of them because I have 2 outputs going into my observer, right? So I need 2 sets of gains for it. All right, so I have 2 inputs, 2 outputs. Handles it just fine, right? In this case, I have now 2 outputs here. And I can put these into a regulator. 2 inputs, 2 outputs. Reg does just fine with this. So if I say this, remember this is 3 equals reg of our original system, which I have not redefined. I'm going to do that. System. You can see that the A matrix is the same, B matrix, 2 of them, C matrix 2. D matrix I have to have a 2 by 2 now. Right? Because there are 2 inputs and 2 outputs. All 0, doesn't matter. And you notice that I didn't change my D matrix, but it was smart enough to fix it for me. That was good. It's some older version of the error there. So let's take R sys equals reg of system Regulator is still the same as our C matrix. It's still the gains of our states for the controller, 2 of them there. B matrix 2 by 2 because that's the observer Y. 2 Y's going into it, right? Y is to the regulator, Y is the input, right? U is the output, so this is the, basically the observer gains part, that's the controller gains part. And here I can find the whole pose of the system. Feedback. Minus 2, I think those are the right numbers. And again, same type of thing. Now, notice what happens if I try to compare it with the other. I still have the other state's step responses held. Gives me an error. Reason being, gives me 4 figures. What are these 4 figures? Sort of labeled there. This is input 1 to output 1, input 2 to output 1, input 1 to output 2, and input 2 to output 2. All right, so you just have 2 inputs, 2 outputs, have 4 plots. And you think that one of them might be position, the other one might be velocity, and it doesn't matter. All right, make sense of this? Questions on this? Yeah.
We talked about inputs and outputs and the relation between the two. Could you explain how you can have like velocity input going to a position output, like look at those combinations you said?
Well, say this is a position, this is velocity.
Yeah.
All right. And I have right, 2 outputs underneath my output actually is each state in this particular maybe some scale of that. But I have to find 2 inputs. Now this could be, it is the same, desired theta. And this could be desired omega. So none of them I say, I want to put it in this position, but I also want this velocity. All right? So it opens up, I can actually command every single state, every single thing in here, if I so wish. All right? That makes sense for that? But notice that this input affects both these outputs. All right? And this input affects both of those outputs. So it can get kind of messy here. We're going to come back to this style when we talk about the quadratic approach, the linear quadratic regular approach, where I will actually try to make controllers to make my states do certain things. Right? Okay. So what you guys need to do in the lab, actually the simplest part, you need to, I think it's this, implement this into Simulink. Right? Because you're going to be creating, and that's a single input, single output system in the lab set up. This is my regulator. It produces U. So I need to take from my AD in, they handle input to the system, or actually it's from the controller of it, is the input, my regulator, output of it is what drives the plant. Right, so essentially we have the input, and this can be a state space system. I can't remember what we call that in MATLAB or Simulink. There's a thing to do. This is like it, drive the system. And essentially you can do it through blocks. Right? inputting, this is Y. You create this, if you, I can't remember the exact command, if you look in the library for Simulink, there's SS, looking at that state system. And open it up and you put in the A, B, C, and D matrix. I think it works fine with the Pointer system. Pointer is funny about summary. I think that would work. Otherwise, I'd have to create it. Now, you don't, also you don't have a second order system. We model this as a second order system. So it's a little bit simpler than a full order. You can also do it just straight simulate if you wanted to do it each block. How would you do that? Let's do it for the second order work. It's messy. Simulate. Say I have a this is from Mary Hood. Making up some numbers here. Inputs, Y. It goes to Y. B matrix, these are all for the observer. These are actually feedback gains in C matrix. Okay. So, let's do it times the B matrix, and you can have, I think the symbol in Simulink is this. Triangle like an amplifier. So this is 2 times Y, is 4 times Y. Okay. Back what is the equation for solving here? Y, if you will. Those are the equations for solving. I have that part. That those are the summation, and the summation and Simulink that usually uses the circle. Okay. And those are those positives. Plus ones there. Up to this is, and in MATLAB, or Simulink, the symbol for an integrator is a block with the acid. We're creating here, this is x1, estimate dot, x2, estimate dot, integrate is x1, estimate, x2, estimate. Right? Let's solve these equations. x1 is minus 2 times x1. And minus 3 times x2. x2 is 4. And that's a plus sign. This times 5 minus. Right. And then these two times minus 3. Minus 4. That would be the Simulink picture for this guy. And it'll actually go out and calculate this thing real time. But either way,